Good morning to all of you. Today we will discuss a topic of multi-stage implementation of sampling rate converters. First we will see what is the need of multi-stage conversion of sampling rate conversion. Okay. So normally suppose if the interpolating factor L and decimating factor M, if they are much greater than 1, suppose if M value is greater than some 10 or 50, 100 like that in some digital signal processing applications, we need such type of large value of M and L, decimating factor and interpolating factor respectively. So in such case, direct implementation of the sampling rate conversion by large value of M and L is computationally inefficient. That point is an important point. Okay. So when M is right here, when M is much greater than far greater than 1, L is also far greater than 1. M is the decimating factor, L is the interpolating factor. If M is very much greater than 1, L is very much greater than 1, then implementing the sampling rate conversion in single stage is computationally inefficient, which means suppose implementation of this in single stage is computationally inefficient. Okay, computationally inefficient. Suppose example, you take example as a suppose M is 10. So 10 is greater than 1. 10 is much greater than 1. Even 100, if you want to implement 100, M is 100 like this. L can be 10 or 100, or it can be some other value not equal to 1. In that case, implementing directly like this, directly in one stage. Suppose I want to down convert by 100. Suppose this is x of n, this is yn. Okay. Now implementing down conversion or decimation by 100 in single unit, it is not an efficient mechanism, because at the same in a single block, so we have to discard m-1 samples, because decimator what it will do, decimator decimates the input sequence by m-1 samples. So if m is 100, so 99 samples we have to discard in a single block. That is maybe hardware point of view, it may be it is generally computationally inefficient. Okay, that is why people try to use multi-stage implementation of sampling rate conversion. Suppose I want to convert from one sample, suppose one sampling rate, so x of n is there. If that x of n, if you want to down sample it by 10, so instead of downsampling in a single stage, I will implement in multiple stages. That is what is multi-stage. Multi-stage means implementation of the sampling rate conversion in multiple number of stages, more than one stage. That is called multi-stage implementation of sampling rate conversion. Okay, I hope all of you clear about what is a multi-stage implementation of sampling rate conversion. Now we will see how to implement practically these multi-stage implementation of sampling rate conversion in terms of decimations as well as interpolation. Okay. First, coming to this, x of n is my input sequence, and fx is implemented by fx is some quantity to represent this x of n. Now, so this is a interpolator, first interpolator. Okay, first interpolator L1, and what it will do is x of n is upsampled. You see the arrow is upside, that is why we say that it is a upsampler. Okay, already I have explained about this in the first class. Upsampler, L for upsampler, so therefore it is an upsampler, first upsampler, and output of the upsampler. So here what you have to understand, L1 means, so it is a upsample, the x of n is upsampled by L1, which means, so L minus 1 zeros are inserted between every two adjacent samples. Okay, every two adjacent samples, L1 minus 1 samples are inserted. Okay, after that, now the sampling rate is increased. X of n upsampled, so sampling rate is increased. So then what happens is, here you will get, so the upsample signal. Now that upsample signal is passed through this is anti-imaging filter. Okay, anti-imaging filter. Okay, what this anti-imaging filter will do is, so it will remove the unwanted images which are replicated in the upsampled signal. Now, so what you get, L1 fx. Okay, that fx is x of n. So therefore, so this fx is multiplied by L1 because of this upsampling. After that, so we have a second stage. Second stage upsampler by L2. Then second stage anti-imaging filter. Okay, after that, so what we will get, L1, L2, fx. So H1n is the anti-imaging filter. It will remove the unwanted images. Then we get L1 fx. After that, L2 is the second upsampler, and the second upsampler will do upsampling by L2. Okay, so this L2, after this L2, what you have? See, L1 fx is there, and this L2 output of L2 is passed to the H2n. Now H2n output is L1 L2 fx. L1 L2 fx. So this L1 and L2, they are multiplied here, multiplied fx. Input is fx. So therefore, like this. So if you closely observe this block diagram, the first one, multi-stage implementation of interpolators. See, if you want to convert a sampling rate conversion in multi-stages, what we are doing, we are upsampling the signal and connecting that upsampling output to the input of the second upsampler, and second upsampler output connect to the third one output is connected as the input for the fourth one, like that, and so on. Finally, so we will implement a last upsampler, final upsampler. This is the nth upsampler. Okay, nth upsampler. So it will upsample the sequence by ln. What is the meaning of that? So ln minus 1 samples or zeros are inserted between the two adjacent samples which are present in this. So L1, L2, fx. Now after that, finally this the sequence is passed through the final filter, that is Hn of n, where capital N indicates the number of stages in the filter and number of filters. All these are anti-imaging filters. Now finally, you see final output yn. So this yn is L into fx. What is L? Where L is L1 into L2 into L3 and so on Ln. It is the product of all these interpolating factors. Final L is the product of all the interpolating factors. So that is how you can get the multi-stage implementation of sampling rate conversion, or multi-stage implementation of sampling rate conversions. Okay, now try to implement, we try to see that what happens in this. Now, so mathematically we can write this. L is capital, this L is what? Interpolating factor. overall interpolating factor, this L. This L is, so pi, so this pi indicates product. It indicates product of the numbers. Suppose see product. So now I value varies from 1 to n because 1 is here and n is there. So 1 to n, lower limit is 1 to n, Li. So now what happens if you expand this? What you will get? L1 into L2 into L3 and so on Ln. That's what you will get here. So that entire thing is implemented in a simple mathematical equation that L is equal to pi, I is equal to 1 to n, Li. Okay, the pi symbol indicates here the product of the numbers. Okay, so this is how we implement multi-stage implementation of upsampler or multi-stage implementation of interpolators. Suppose see example, if you take example n value 2. So if you take that n value 2, see now I want to implement see n is I is equal to 1 to 2, I is equal to 1 to 2 Li. So this is a capital I, capital I. So therefore capital L. So capital L is equal to, so what is the meaning of this? L1 into L2. L1 into L2. So what is the meaning of that? So I am implementing this capital L final stage interpolation by using two interpolators, two sub interpolators, L1 into L2. Suppose example you take, I want L is equal to 10. I want to implement L is equal to 10. So it is a actually if you want to implement this 10 by using multi-stage implementations, what we have to consider is, you consider L1 is equal to 2 and L2 is equal to 5, like this. Okay, L1 into L2. Now L1 is 2, L2 is 5. Suppose I want to implement it by suppose 30. So therefore now what I will take is, see, L is equal to L1, L2, L3, L1, L2, L3. So now see, so 2 so instead of that you take 3 into 2 into 5, like this. Okay, 2, otherwise 3 into 2 into 5, 2 into 3 into 5. Okay, 2 3s are 6, 6 5s are 30. Okay, like that. Suppose for L is equal to 30. This is for L is equal to 30. Okay, in the first stage, I will take this L1 as 2. In the second stage, I will take this L2 as 3. In the third stage, I will take L3 as 5. Okay, like that. So we can, this is a very compact representation, and also it is a computationally efficient method, because implementing 30 in a single stage so requires different means it is a computationally, you need more multiplications, you need a computationally, it is a computationally inefficient. So that is why what we do is simply you find the factors of that value, L value, and so you implement each L value, sub L value at a corresponding blocks. Suppose see L1 is 2 and then L2 is 3, then L3 is 5. Example, if you draw the block diagram for that, example, I will draw this. See, now we concentrate only on the what I am writing. See, now suppose L is equal to 30, as we have seen, L is equal to 30. Final, I want to upsample the sequence x of n by 30. Then what I will do is, you take L is equal to L1 into L2 into L3. 3 stages. 3 stages multi-stage. Now you see, L1 is 2, 3, 2 into 3 into, so 5, 2, 3, 5. So total, however, you will get 30. So now how to implement this? See, first you take xn and you upsample it by 2. Then you pass it to the filter, anti-imaging filter H1 of n. Then you apply as the output, this output as input for the second upsampler, and the upsampler value is 3. Then so H2N, second anti-imaging filter. After that, then 5, upsampled by 5, and this is the last filter. Last filter, that is H3N. H3N. So this is your YN. This is the YN. So therefore this is a three-stage implementation for L is equal to 30. Three-stage implementation for L is equal to 30. So therefore these are the possible factors which you can use to implement a interpolator for L value 13. Okay, like that you can do the multi-stage implementation, and the formula for implementation of multi-stage is simply whatever we have seen, that L is equal to, so pi I is equal to 1 to n, so Li. This is the formula which we have seen already. Now see, so this 2 into 3, 6, 6 into 5, 30, and this anti-imaging filter, so however this anti-imaging filter and anti-aliasing filter used in Decimator, both are having the same sampling rate, so that is why it is a low pass filter for this H1n, H2n, H3n. So therefore at the output of every stage, every upsampler will have a one anti-imaging filter, that we have to remember, right? So once after converting from low sampling rate to high sampling rate, otherwise interpolating once, after that we will have an anti-imaging filter, like that you can remember it. So this is how we can implement multi-stage implementation of the sampling rate conversion, especially interpolation. Now coming to the second one, that is multi-stage implementation of the this decimation process. Okay, multi-stage implementation of the decimation process. You see this. What is decimation? Decimation is down sampling. Okay, decimation means down sampling. Decimation implies down sampling. Down sampling. Okay. So now you see this x of n is the input sequence. Same lines on the same lines will continue here also. X of n is the input sequence. This x of n first pass through the H1n. What is H1n? H1n is the anti-aliasing filter. Okay, anti-aliasing filter. FILTER, anti-aliasing filter. So therefore, first if there is any high frequencies present in the input signal or input sequence, that is filtered out by this anti-aliasing filter. After that, so instead of having a single stage completely down by 10 or 50 or any other value 100, what we do is we do it in first stage some decimation. After that, so we decimate further, and in the final stage we decimate again further, like that. Okay, this is a capital N. So like this we can do the decimation as multi-stage decimation. So now H1 of n is the anti-aliasing filter. So this anti-aliasing filter, the purpose of this anti-aliasing filter is to remove the high frequency components which pass outside the required frequency. Okay, now that H1n is downsampled by M1, and that M1 is passed through the H2n, and H2n again the second anti-aliasing filter, and here, so therefore here what you will get Fx by M1, Fx by M1. Okay, at this stage you will get like this, Fx divided by M. Okay, after that H2n, and H2n output is passed through the second decimator, and then Fx by M1 into M2 you will get. Okay, like that. So last stage, so Hn of n is the last stage anti-aliasing filter, and Mn is the last stage decimator. Okay, so therefore here also same. So M is equal to, final capital M is equal to pi is equal to 1 to n mi. So with this pi indicates product or multiplication, right? Product of all the m's. So m is equal, suppose n is 3, capital N is 3, so m1, m2, m3 you will get. So therefore finally yn is fx by m. So where fx is the input sequence, m is the overall decimating factor. Suppose in the same case, you see in the previous one, m is equal to, we have considered l is equal to 10. Here also you take m is equal to 10. So when m is equal to 10, so first you down convert it by 2. Then you pass it, so first you pass it through the anti-aliasing filter, you down convert it by 2. Then again you pass to the second filter, second anti-aliasing filter. Then you downsample again by 5. Like that you will get. So 2 into 5, 10. So therefore fx by 10 you will get in the output sequence. You can try the same examples whatever we have seen in the previous example. Like interpolator example, you can use the same example and you can try to implement it and try to implement on your own. Suppose you take L value, suppose M value you take 30. So then what we need 2 into 3 into 5 means 3 stages. Here only in 2 stages you can compute for m is equal to 10. If you take m is equal to 30, so 2 into 3 into 5. So like that you will get a total. So m value 30. So then finally you will get fx by 30. That is how you can implement. So multi-stage implementation of sampling rate conversion. So here sampling rate means sampling the sequence x of n is down converted by 10. Okay, like that. So what is the meaning of down conversion? Suppose if you have a m value 2, so what happens? M minus 1 samples are discarded. One sample is discarded. So then, 5 minus 1, 4 samples are discarded. Like that. So we can implement any number of down conversion, whatever may be the value of m, you can down convert it, but it not in one stage.